Hello and welcome. My name is Dr. Heather Brown. As Director of Grant Writing and Publications at the University of Missouri-Columbia, I am pleased to welcome you to the 4th Annual Federal Research Update webinar. This event is sponsored by the University of Missouri-Columbia, the National Association of College and University Business Officers, and the Florida High Tech Corridor Council, an economic development initiative of the State University System of Florida. We're so pleased that you could all join us today. If you have any technical problems during this broadcast, please send an email to federalupdate@missouri.edu. And again, if you want to ask questions of our presenter, you can send us questions at any time during the presentation. The same email can be used, federalupdate@missouri.edu. And again, we have viewers joining us from across the country, so instead of using specific times, we are going to use phrases such as top of the hour and bottom of the hour. And just a reminder, we did have to reschedule some of our Monday and Tuesday presenters as the result of Hurricane Sandy. And we will have 2 additional presentations this afternoon that were not originally scheduled. Emily Lindy and Scott Cooper from the NIH are going to be talking next. And David Hahn from the Office of Naval Research will also be coming in at 3:30 p.m. Eastern Time, 2:30 p.m. Central Time. So I am very greatly honored to introduce today Dr. Thomas P. Russell. Dr. Russell, a member of the Senior Executive Service, is Director of the Air Force Office of Scientific Research. He guides the management of the entire basic research investment for the Air Force. He leads a staff of 200 scientists, engineers, and administrators in Arlington, Virginia, and foreign technology offices in London, Tokyo, and Santiago, Chile. Dr. Russell, I'm turning it over to you.
Thank you very much. It's a pleasure to be here and have the opportunity to talk to everybody about the Office of Scientific Research and the Air Force's Basic Research Program. So what I thought I'd do is go through some view graphs to kind of give some flavor of, what the Air Force Research Laboratory and AFOSR is interested in, the types of work that we fund, and maybe a little bit about how we actually execute our program. And in that process, if people want to ask questions, because it helps me understand, what the audience would like to actually hear about, I can change and morph this presentation to meet the desires of the audience. So I like to start off with why the Air Force invests in basic research. There's recently been a Defense Science Board report which came out in January of 2012 looking at the overall basic research portfolio of the Department of Defense. But really, the reason the Air Force funds basic research is primarily driven by 3 major areas. One is that we really, through the basic research program, probe today's technology limits. And this really ultimately leads to the future technologies important to our national defense as well as into our society. We also attract the most creative minds to the field, which are critical for the Department of Defense and for the Air Force in our interests. And so people like Secretary Chu was a former principal investigator as part of the Office of Scientific Research Program, and more recently Andre Geim, who won the Nobel Prize for graphene, are 2 examples. And a third one, which we often don't actually think about very often, is it really creates the knowledgeable workforce in fields that are critical for the future Department of Defense interests. So when we fund basic research, what we're really doing is we're actually funding the future STEM workforce at the graduate and undergraduate level for the department. And we're training them to understand the basic scientific fundamental principles of areas that are important to the department. And the reason this is important is because, the Department of Defense is actually one of the single largest employers of scientists and engineers in this country. And through these programs, we're not only trying to, identify the future, identify new opportunities, probe today's technology limits, but we're teaching individuals to do that, as well as teaching individuals what are the new opportunities in the department where we need help, not just in our laboratory system, but across the entire S&E workforce. The other thing I often get questions about is, what's the difference between a DoD funding agency and the National Science Foundation? So we're different in the way we actually operate our business, but one of the things that I'd like to start off with is that really this country has established a basic research program that's diverse, which is spread across multiple agencies. And because it's spread across multiple agencies, it actually creates a diverse approach in the way we actually fund basic research and the types of things that we're actually interested in. And so the strength of the program across our country is really the diversity in the way we all manage our basic research portfolios, because we don't all do it the same way. We actually use different procedures for selecting proposals. We use different procedures for funding research. And so because of that, that actually gives our nation an opportunity to have multiple approaches to looking at the best science that one can fund. So what this view graph shows is that we at the Air Force we're really focused on a mission orientation. And I think you'll hear from, I heard just a few minutes ago, the Department of the Navy. They as well also have a mission focus in their basic research. But that doesn't mean that we're not interested in funding the basic fundamental sciences. What it means is that we're trying to actually solve what we perceive to be future technological problems of the Air Force. And in many cases in the basic research program, we're actually trying to lean far enough forward that we're thinking about things that the Air Force is not thinking about itself at this point in time. So this list of documents on the left-hand side really identifies some input that we've been getting from both the Air Force and the Department of Defense. And the 4 white ones on the bottom left really identify 3 reports that have come out of the Chief Scientist Office for the Air Force, which was Tech Horizons, Cyber Vision 2025, and Energy Horizons. And the final one is actually from Dr. Robin Staffan's office, which is the Basic Science Office in the Department of Defense. And this identified 6 disruptive basic research areas that the department identified where there may be game-changing opportunities to profoundly impact the future department and its capabilities. And what this view graph really shows you is not the funding today when these documents against these documents that we're funding, but really the funding we were already spending in the areas being identified as crucial to the future of the Air Force or the department. So the organization was already leaning towards a lot of the different opportunities where we now start to identify where there are abilities to impact the future of the department. And so what that tells you is that we are a mission organization, but what we really are looking for is the best science and the best researchers that we can find across the globe to address areas or create new opportunities for the Air Force. All right, so how do we do that? So our mission as the basic research manager is to discover, champion, and shape the basic research that will basically make today's Air Force obsolete. And so what I mean by that is that we're really pushing the frontiers of science, trying to identify new scientific discoveries that will really change the Air Force of the future. And by changing the Air Force of the future, we'll actually make our current Air Force obsolete. So we do this through 3 primary goals. The first one is we're really looking to identify basic research opportunities both here in this country and abroad. We do this with 60 program managers who are actually scientists and engineers across the globe, 22 of which are overseas in the offices in London, Tokyo, and Santiago, Chile. And then we sponsor lots of workshops and symposium to bring scientists and engineers together to actually engage in discussions to actually advance the scientific community. We foster revolutionary basic research by actually issuing grants to institutions and actually to individuals. We don't fund institutions, we actually fund individuals. Today we have about 1,300 extramural research grants at over 200 universities across the United States. There are also a couple hundred universities across the globe which we're funding as well. We also have a research laboratory within the Air Force Research Lab in the Air Force, and there we fund about 313 projects. And then total, there's roughly about 1,900 principal investigators. And if we go back to this idea of this really being, part of a STEM program, you can see that in an annual basis, we support 3,500 graduate students and over 600 postdocs a year as part of the program. And then finally, as a research organization looking at science, the question really is are we transitioning this science to the department or into industry? And this is a very difficult topic to really identify what does a transition mean. So let me spend a few minutes on that. So a transition in a venture capitalist world would be to actually innovate something. So a venture capitalist will invest in something so that they can actually create a new opportunity. And in that venture capitalist model, what we're really looking for is a return on investment. And the innovative companies are typically those companies that are invested in through a venture capitalist. And innovative companies really do exploit science. They don't often generate basic fundamental science. What they really do is they exploit science to actually innovate. And so that's what the venture capitalist model does. But there's some funding in venture capitalism called angel funding. And angel funding is really just spreading money out to identify new scientific opportunities. And so at AFOSR, we're not just spreading money out, as I mentioned, we're doing it from a mission perspective, but we're actually funding that basic fundamental science so that others can exploit it and use it to actually innovate new technologies, new capabilities, or new opportunities in their companies or in their institutions. And so the transition of basic research is when we have actually developed something or identified enough science that others recognize the potential of it, and then they invest their own money, their venture capitalist money, into that science to actually create a new opportunity. So they're the ones that are actually getting the return on investment. And so we actually, believe it or not, have about 900 of these a year, and we measure this on an annual basis. And our primary transition path is the laboratory, which we fund at the Air Force Research Lab in those 313 intramural projects, because they're knowledgeable of the things that are of interest to the Air Force. And so they actually, working in our portfolios, work collaboratively with the faculty members across academia. And they actually understand a lot of the things that the Air Force would like to eventually develop. And they have an idea of how to apply the science in an Air Force specific model. But we transition a lot to industry, other academia, other federal agencies. And so it's a very robust program. And on top of that, we also manage what's called the STTR program, which is a small business program. This is focused on building partnerships between academia and small business. And it's a program we manage ourselves because a lot of times we identify things that are ripe for that transition, and we use this program as a way to actually help accelerate things where we think there are potential opportunities for this investment of a venture capitalist investment where maybe others have not picked them up at this point in time. Okay, so just to kind of touch base on the academic community, so the broad engagement is really across the United States, and this shows a weighted distribution roughly of the different institutions we fund in the states. Our top universities that we are funding based on dollars are on the left-hand side. As I mentioned, we're looking for the best and brightest we can find in the portfolio, and on the right gives a representation of some of the active members of our research program who are funded by AFOSR. There are currently 4 Nobel Prize winners, one of which is on the President's Council, PCAS Council. There are actually 2 PCAS members in the portfolio. A lot of professional society fellows. We have lots of young investigators. But the reason I show this is because in academia, this is really where a lot of corporate basic research in our country exists today. And so the industry has moved out of the basic research organizations within their own institutions, because again, this is not an area where you have a good return on investment. And so what's happened over the last couple of decades is academia has set up tremendous numbers of small businesses. Many faculty members today actually have small businesses associated with their academic programs and research granting institutions. In fact, the majority of the high-tech small businesses that exist in our country are tied to the academic institutions. So one way of enhancing this transition I described is to actually fund broadly the academic community to discover new scientific opportunities, and then have them also through the small business vehicles use that opportunity to transition or innovate through that science. And that's again why we get a lot of transitions through the academic institutions and not just through the Air Force Research Laboratory. So when I fund the Air Force Research Laboratory, it's really about improving the organic capability of the Air Force. We have an intramural program we fund, as I mentioned. It's a competitive program. Funding is not just given to the laboratory. They write proposals just like everyone else does. They're peer reviewed. That peer review process identifies the best work that we can fund, and then we support that research within the laboratory. And what this does is it really ensures that the Air Force has a healthy in-house basic research capability, primarily so that they can engage with the broader academic and scientific community and do the things I described of helping transition science into the needs of the Air Force. We also have workforce development programs. We'll talk maybe a little bit later about postdocs. We fund about 80 postdocs per year in the laboratory. There are summer faculty fellowship opportunities where faculty members from across the country actually go to the Air Force Research Laboratory and do summer appointments at the laboratory, working side by side with Air Force Research Laboratory investigators. And then, of course, they also bring students with them. So last year we supported about 22 students. We also do a lot of international personnel exchanges because we do believe that the science has become global, and so we need to actually have a better engagement from the international. And then more recently, we've started to develop what are called centers of excellence. These are areas where the Air Force, where the laboratory may identify new technologies that they need to move into, don't have in-house capability. So they build some academic engagements and centers of excellence, helping develop new workforce partnerships between academia and the laboratories, and then helping us grow a new capability into the lab. And we don't support just the lab. We also have some programs supporting the test and evaluation community. We also support the Air Force Academy, so that cadets who are going on with military careers get basic research experiences and doing research in centers of research at the Academy. And then there's a master's and PhD degree granting institution, AFIT, which we fund as well for postdocs as well as research, so that military members can get advanced degrees in science and engineering as well. All right, so let's touch a little bit on international. Really, the international program is a program focused on about $20 million a year, where we're actually funding institutions around the globe. This building international relationships really, in many cases, is about avoiding technological surprise. And so there are a lot of opportunities where we, as basic researchers, can actually engage, overseas, where the military or government-to-government interactions are much more complicated. And so on the right is just a subset of some of the activities that we've been working collaboratively with our international partners. A lot of work in nanomaterials in Taiwan and Korea. We've been doing some extremophile work in Chile, bio-inspired flight in India and the United Kingdom, and then of course areas like quantum information sciences and then ultra short pulse lasers in Europe. And in the DSB report, which I mentioned earlier, there is actually a very strong recommendation that the basic research organizations need to actually increase funding to academic institutions overseas to actually increase those partnerships, both with the government researchers, but also to help enhance our partnerships across the academic institutions I mentioned a little earlier. And so to finish up that discussion, what I thought I'd do is just provide you some data we've pulled on basic research publications. And so we pulled the literature on English journals. And the bottom map actually represents a decade ago, the publications in English-speaking journals across the globe. And so you can see the United States actually produced about 26% of the articles published in English. And in 2010, that number's actually dropped to 18%, and you see a large growth in the Asian communities in having more publications across the literature. And really what this is meant to do is just kind of emphasize that this is a global scientific community today. It's not a national scientific community. And if we're not engaging from a global perspective, then we're actually missing many opportunities of discovery which are important to our country, are important to our nation, and important to the Air Force and the Department of Defense. So let's touch just a little bit on the budgets, because I often get questions about budgets. So the Air Force actually manages two budget lines for basic research. The one on the left is what is normally referred to as Defense Research Sciences, so it would be the Air Force 6-1 Core Program. In this, what you can see is a lot of the things I've talked about, the postdocs, the centers of excellence, that workforce development piece, and the AFRL intramural. That runs about 30% of our entire portfolio in the Defense Research Sciences. That's funding the laboratory. More than 50%, about $200 million a year, is spent in academic institutions. As I mentioned, there's about $20 million a year funding research and partnerships between U.S. researchers and international researchers. And then there are operating expenses and a few other things. From the OSD line, which we manage, all the services actually manage what is called the University Research Initiative line, which was established by Congress in the 1990s. There are several special programs here. The Multi-University Research Initiative, which is the green piece here at AFOSR, that's about $71 million a year. And here there's a program where we bring together multi-university teams to solve programs or to solve problems of definition through topics. We also fund the National Defense Science and Engineering Graduate Fellowship Program, where we're supporting graduate fellowships and stipends to actually do research across the academic community. Assure, which I'll go into a little more detail as well, is funding we actually manage to actually work with NSF in the REU program, the Research Experience for Undergraduates. PCASE, which is the Presidential Early Career Award for Scientists and Engineers. In the department, our PCASE winners actually are given a 5-year grant award to actually do research while they're after being selected as a PCASE winner. And then one thing which is really important in this portfolio, which we are trying to grow a little more, is the DURIP program. The DURIP program is really the department's only funding opportunity to have for instrumentation in academia, and it really supports all S&T, not just the basic research. So it's actually a program meant for instrumentation to support all research in 6.1 through 6.2, 6.3 in the S&T program. So describing a portfolio of this size is almost impossible. And because there are so many projects and so many neat things that are ongoing, it makes it very difficult to pick and choose. And then when you want to pick one area, you get the question of, well, why did you pick that versus something else? And so I've started to try and give a different kind of flavor of what the diversity of the basic research activities are within the portfolio. And I will give you some cool examples as we go along. But I think this kind of represents more of the breadth of the portfolio. So we fund basically 3 major activities across the program. So the first one is really an area which defines the things where we are leading. So I picked hypersonics research. There are several other ones that are actually ongoing in our portfolio. But in hypersonics, the Air Force Basic Research Program is effectively the nation's lead in this basic research in combustion materials and fluid dynamics. There are other people we partner with, NASA, the Navy, Department of Energy. So we are not in this alone. But we really take the lead in this effort, and so we're committed to the basic research associated with hypersonics. And so there's a breadth of these types of programs in combustion and other areas where our portfolio has that major lead and focus. Another area which is important to us is where we think the rest of the world may be out in front. So, as I mentioned, a lot of science today is being done overseas. It's not being done in the United States. And because of that, there are many, many discoveries which are occurring in the international community. And so one that I've mentioned here is a few years old now is the new superconductors, the iron-based superconductors, which were actually discovered in China and Japan, which has revitalized some of the superconductivity work. And again, looking to see, can we actually get to room temperature superconductivity? And so this work, we are funding some in our international programs, but we then build programs here across our nation and academic community looking at superconductivity again, and can we actually potentially identify new opportunities here which we didn't have in the last revolution in superconductivity. And the third one really are investing in what we might consider to be potential game changers. And so the ones that are often described are the ones that I mentioned earlier for the basic research, disruptive technologies, which are quantum information science, social cultural modeling, nanomaterials, metamaterials, plasmonics. And I chose one that was slightly different. So in this case, we've done a tremendous amount of work looking at bio-inspired systems, and not to mimic biology, but to understand how biology has actually evolved to solve some problems. And in many cases, solves problems very inefficiently. So this work shown here on the bottom right is some work at Brown University where we've been looking at the aerodynamics of bats and looking at their adaptive structures. They have feedback loops, the hair follicles on their surfaces where they actually can measure the flow over the surface. They can actually adapt their wings. They can manipulate their structures to optimize the fluid dynamics. And it turns out they're actually one of the most efficient flyers in the world. And so you can understand the reason why maybe an Air Force or our country would want to know this, because it might help us improve efficiency in air flight, which would reduce fuel economy in in aircraft and other areas. But the example I gave is not that. So one other interesting aspect of bats is that they navigate through sonar and they do really the final engagement for prey capture using sonar. But this capability only lasts for a distance of 15 to 20 meters. So then one might ask the question, well, how do bats navigate for miles? Because you can see many pictures where bats come out of tunnels and they migrate, and so they're navigating through other mechanisms beyond looking at typical things we describe as sonar. And so the way they do this is they really have some mechanisms where they can actually sense the Earth's magnetic fields, and so they do magnetic field navigation. And so it would be very interesting if we could actually understand how bats and other animals actually can sense these environments and then do things like navigation or other things through these sensory systems that we don't really fully understand today. And again, we don't want to make a bat. What we just want to do is understand how the bat evolved or how nature has evolved to actually solve some complicated problems. All right, so often we're asked about the program, so I'll go through quickly the portfolio a little bit. We're currently divided into 3 directorates. The directorates are currently named based on scientific disciplines. That's typically to help with the engagement through the academic community. So if you're a chemist, then you would probably first interact with, the Aerospace, Chemical, and Material Sciences Directorate because it says chemistry in it. Or if you're a physicist, you may actually look at physics and electronics. Underneath these categories are things which we have defined as some of our focus. What are the focus areas of interest to solving Air Force missions? And what we are doing here is we're trying to bring the multiple disciplines together to actually solve these multidisciplinary problems, because most of the major advances will occur at the fringes or the overlaps of these disciplines, and it's where those major advancements will actually occur. So I'm not going to go through each one of these. This is the Aerospace, Chemical, and Material Sciences Directorate. These are the current trends within the portfolio. The focus areas are the blocks. So in this case, it's aerostructure interaction control. So this would be where you look for things like turbulent laminar transition if you're a fluid dynamicist, air elasticity and structural dynamics, some integrated modeling, unsteady aerodynamics, how we do flow control, a whole host of things which you would mostly think in the aerospace science areas. Energy, power, and propulsion, a lot of areas like combustion, catalysis. We're interested in thermal sciences, not in thermal management. Thermal management would be the application of thermal sciences, and thermal sciences would be interested in things like looking at a phonon-electron coupling. Can we actually understand the fundamentals of those processes? How do phonon electrons couple and move within materials? Could we then design those materials so we can actually manage how the thermal energy moves within materials? This clearly also would play a substantial role in energy harvesting if I was trying to develop better solar materials for solar cells. Complex materials and structures. Many years ago, before the Materials Genome Initiative, we moved into the idea that materials today are really not monolithic. They're really three-dimensional. They're complex, and so what they really are is they're n dimensions in versatility, 3 dimensions in space, and so you can actually create the functionality of materials, whether it's structural or whether you want them to be self-healing or whether you want them to actually have adaptable so that they might actually be morphing. These really become 3-dimensional in nature, and so they're really complex materials and structures. The experimental techniques to actually understand these materials are not well understood. We do have lots of 3D capabilities. A lot of it is mostly in 3D reconstruction. One area which we would like the scientific community to start thinking about is what are the temporal and spatial resolutions we can do in real-time measurements. So if I want to look at failure of a material and crack propagation, wouldn't it be great if we could actually measure the three-dimensional material, identify where a crack starts, and watch it grow in real time so that we can actually use that experimental data to validate the models and the tools that we actually use for predictive capabilities. Some things which have come out of these programs, carbon neutral fuels. This was some funding which we had done at Princeton and I believe Caltech, where we were actually looking at catalysis, where one could actually produce alcohols or oils, or alcohols, I'm sorry, from really looking at CO2 water reactions just by using sunlight. So kind of replicating photosynthesis. And this would be an area where I would mention is a transition. So we funded this work. It looked like there was a potential opportunity with some new catalysts to actually rejuvenate, some of these ideas, and NSF and EARPA, which is the Energy ARPA, have actually set up centers focused on trying to develop this science. And so it's an area where we're still looking at some of the fundamental catalytic problems, but we're actually now no longer investing large dollars in understanding how do I maximize or do the efficiency, because someone else has actually started to invest there. We do a lot of novel, flexible, low-cost solar cell work. You can think of flexible solar cells and for satellites, or you might want them for skins on vehicles. And so if you wanted a micro vehicle, you don't want to have any parasitic weight, so you'd really like the skin of a micro air vehicle to really be a solar cell, so it'd have to be flexible, adaptable. And then resistive coatings, and looking at ways of actually having things that will repel both oil and water. And there have been some materials which have been designed that can be used on clothing today, where you can dip them in clothing, dip clothing in them, and they'll actually repel both water and oil, which has a huge benefit in a lot of applications. So in the math, information, life sciences area, there's a lot of work in information sciences and complex networks, looking at can we actually have adaptable polymorphic networks in resiliency, or we're really looking for the idea if you wanted to defend a network today, it's hard to defend, but what you really want to do is have resiliency and be able to operate in your networks while they're under attack, as opposed to having them being shut down. And so this develops a lot of complex mathematical problems and trying to understand fundamental mathematics, algorithms for architectures, and then can we develop advanced architectures? We're interested in understanding how humans make decisions and how machines make decisions. And so there's a program in robust computational intelligence, trying to understand beyond just machine learning, and really understanding the foundations of autonomy. So if we're going to have autonomous vehicles someday driving around like Google has today on the West Coast, how do we really trust these systems? How do we actually, ensure that those autonomous vehicles are really, operating in ways that we understand and that we can actually accept? And then, what are the effects of this on our culture, and what are the effects of these interfaces, and how do humans and machines interface with each other to optimize a human being's performance, as opposed to using just the mouse and the computer? Or the mouse, in one case, is one way of actually optimizing that the human's interface to a computer, which was actually developed in the 1960s by a man named Engelhardt at Stanford Research Institute, which was funded by the Air Force Office of Scientific Research. And the idea was to really look at how to interface humans to machines. So I won't go on. A lot of work in natural materials. I already talked about some of the bio-inspired stuff we're doing. The extremophiles is a really interesting area because nature has figured out how to survive in environments where we as humans would never be able to survive. So there are some bacteria that today have evolved to be able to survive in autoclaves. So even though they're supposed to be sterile environments, there are some bacteria today who have figured out how to survive in that. You have bacteria surviving in Antarctica in extreme conditions, or actually at Yellowstone National Park, with the geysers in these highly acidic or highly salt environments. I'm not sure of the time, so I mentioned some things about artificial photosynthesis. So we actually can create devices that begin to actually harness sunlight and begin to split, which I mentioned. There are some applications in using graphene that allows, better direct atomic resolution of imaging, so that enhances our imaging capability. And then there are the social cultural areas really looking at, understanding beliefs and how we actually correlate these beliefs to understanding how one might actually engage with other communities and networks and individuals. And then the final area, going through this in more detail, is physics and electronics. In this case, it's a lot about complex electronics and quantum processes. So we're in the middle of the second quantum revolution, where the opportunities of doing quantum computing exist, which would far exceed any computational methods we have today. But quantum methods are far beyond that. So you can do atomic clocks, inertial navigation, a whole host of opportunities for imagery and imaging. Metamaterials are those things which have things like negative refractive indices, where we can, unlike nature, where you can actually bend light in reverse directions. Graphene, which we've all heard about, has opportunities for completely new one-dimensional electronic devices and sensors. In the area of plasma sciences and high energy density non-equilibrium, one of the areas that the Air Force in particular is very interested in is space weather. What we'd really like to do is have a 72-hour prediction of any disturbances on the sun and what that means to the space environment around the Earth. And this has huge implications in satellite technology. So there was a Halloween storm, I don't remember the year, less than a decade ago, which took out satellites around the world and impacts the airline travel, communications, and other things. And what you really want to do is kind of like what we have for meteorological weather, is have space weather predictability, so that you can maybe protect satellites and assets from this disruption within the space environment. Electronics, communication, lasers, nonlinear optical materials, a lot of work in novel RF devices and communication architectures. Some examples of things which maybe I'll just touch on. One is the quantum memory, so back to the quantum information sciences of the second quantum revolution. So at Georgia Tech, we've recently actually have been able, the researchers there have actually been able to store information and extract information in Bose-Einstein condensates. So you can actually start thinking about these as high density information storage opportunities. The relativistic magnetron, we have codes today where we can actually predict magnetrons and how we actually design and the fundamental physics of these activities as well. So before we move into how we shape the portfolio to the future, what I'd like to do is mention that these are programs of 3,000 to 5,000 projects, and so in any presentation it's impossible to really get a full understanding of the portfolio. So at AFOSR, and I don't think I have a view graph on this, we've actually tried to create a much more open environment for communicating with the academic community and with the scientific community at large. So what I'd like to do at this point is direct you to a web page. The web page would be APAN, APAN.org, I think it is. And if you go to apan.org, you can just search for AFOSR, and on the AFOSR page there are a few things you'll find. The first one is that we hold an annual review, which will be the first week of March, 4 through 8 of March in 2013. Annually, what we do is we actually videocast that as well. So every program manager will stand up in front of senior leadership of my organization, talk about their directions, strategies, things that they're interested in their portfolios. This is videocast, and it's on the APAN webpage where you can actually access that information for the entire year. There's been more than 20,000 downloads of those videos already. Their presentations that are provided as well during that meeting are also available on that page for download, and there's more than 20,000 downloads of those as well. In addition, we are now posting information about the portfolios, identifying who the PIs are in the programs, some of the activities that are ongoing within the portfolio, as well as trying, as our program managers have contractor meetings, we're trying to post information associated with the PIs in the portfolios we'll present. We're trying not to, those meetings are meant to have some pre-publication release discussions, and so in many cases you will not find them being videotaped, and the presentations will actually have any pre-publication materials removed because we want to protect the rights of our PIs in our portfolios. But those things which are, can be cleared and distributed, based on the portfolios, will be distributed on a regular basis so that, members of the community can have a better understanding of what's happening across the AFOSR portfolio. All right, so how do we shape the future? So I've given you an idea of where we are in the current programs. At AFOSR, we've recently started an initiative process where 20% of the portfolio is actually, $20 million of the portfolio is turned over on an annual basis into new initiative directions. And this is meant really to try and enhance and maximize the discovery potential for the defense research environment that we actually live in. And so through this basic research initiative, these are the 9 topics that were chosen for fiscal year 13. And you can see some of the topics that we were describing a few minutes ago. There's, foundations of energy transfer and multiphysical flow phenomena, which is kind of related to understanding, capture of and representation of how do I have cohesive understanding of energy and how energy transfers through materials. The high peak power, ultra short pulse laser interactions with materials. If we're getting into the petawatt lasers and other high peak power laser applications, how do these lasers interact with materials? Cyber, trust and suspicion, so in the cyber environment. I won't read all these, I'm assuming they'll actually be available as time goes on. Trying to look at transformational computing, getting between, looking at novel architectures, hybrid architectures, things like co-design, where if one wants to really do high performance computing, then eventually you need to get some co-design of high performance algorithms and hardware so that the algorithms are actually designed and optimized for the hardware they're going to be run on, and then that hardware may not be just purely digital, it may be analog, digital, quantum, a hybrid approach, maybe something more similar to what nature does. I mean, our brains are not purely a digital process for doing processing or problem solving. There are chemical processes as well as digital processes within the human environment to make decisions. And so again, looking at chemical reactions and endothermic cooling, so in a lot of applications in the Air Force, we use jet fuel to actually cool the engine environments, and so they need to absorb the energy in the jet fuel, so it's not traditional fuel which you might have in a commercial fleet. All right, so I could probably spend the rest of the day just describing transitions. And one of the things that Steve Jobs said, I think at a Stanford graduation, was that you can connect the dots looking backwards, but you can't connect the dots looking forwards. Now, I probably butchered that quote, but it's pretty close. And so what he really means by that is it's easy to see where you've come from. And when we look back at basic research, we can identify many things that we've funded fundamentally that have turned into new applications, that society, the department, and the defense, and everywhere across the globe are actually using today. And but one thing that often happens is we're told that it's always a decades or multi-decade long process. And science today evolves at a rate far exceeding that, and it's no longer a multi-decade process to always see transitions. So I will give you a multi-decade one just to give an example. So original work funded at Stanford on optical parametric oscillators really was the discovery of OPOs, which converts light to different wavelengths. And during that period of time, a patent was filed, which was the laser eraser, which was the ability to erase ink off of paper using a laser. Well, that technology today is actually used to depaint planes. So that's how you actually, one technique of actually depainting planes, especially if they're composite aircraft, so that you can actually take paint off of composites without actually damaging the composite material underneath. So there are many of these types of examples. So in this case, what I chose to do is pick things that are programs that are really still being funded, have only been funded a few years. And they're not ones that are just Air Force funded, because one of the things that I didn't really mention is the services really work very cooperatively together. So the top one is a MURI program at the University of Maryland. It's about rotorcraft brownout. So when a helicopter lands, it kicks up dust. It makes it so you no longer have visual cues and guidance of actually landing a helicopter. It's just called rotorcraft brownout. And so we run a MURI program at the University of Maryland. There is actually also joint work funded there with the Army. And so this is really a two-phase flow problem, looking at particle entrapment and a fluid dynamics problem. And then how do we actually understand this process, and then can we actually develop the models and algorithms to actually model what happens in this brownout environment. And so today, through this program, which is only in its 4th year of a 5-year MURI, these algorithms have already been transferred to the simulators, where people who are flying helicopters today can actually get virtual training flying rotorcraft simulators. And in those simulators, they actually get real-world representations of what a brownout scenario would look like based on the maneuvers that they are actually performing. And that is all based on the work that was being funded in this MURI program, and also with the Army we did jointly. The middle one is about command and control. It's really about how do I communicate. And in this case, it's really about, can I do secure communications? This is a MURI program at Princeton University, and is actually now in its 1st or 2nd year had actually started to develop some mathematical tools for doing software on cloud networks, and how can I actually have reduced failures and security. And this was rapidly transitioned to one of these STTR programs I mentioned to you, of actually taking the opportunity to exploit this basic research, and is now actually being looked at as over the horizon types of command and control in secure networks. And the last one's one I chose through our international program. This is one that's actually a joint funded effort with the Navy. So there's some activity at Czech Tech University in Prague, and they have been working autonomous deconfliction. So if you have an aerospace environment with autonomous vehicles, can I actually do deconfliction of those autonomous vehicles so that I don't have to have people doing the traffic control in those environments? And of course, then Navy would be interested around carriers. The Air Force is of course interested around how do I do air traffic control in bases. And the more important thing is, how do I actually do air traffic control with autonomous vehicles and mixed system, where I have autonomous vehicles and human flight vehicles. And this technology today from the Czech Tech University is actually now being investigated not by the department, but primarily through FAA and NASA, and looking at next-gen as one of the potential ways of doing deconfliction in the airspace for the next generation national airspace that we're trying to solve into the future. So here again, activities that are being funded in the early programs are having potential large impacts across the nation. All right, so I'll go through. We educate the next generation. I mentioned the National Defense Engineering Graduate Fellowship Program. These are tuition stipends of $35K. There's no service obligation. You can find this on the ASEE webpage. If you want more information, you can also find it on our webpage. Assure is our DoD's funding to support research experiences for undergraduates through NSF. So it's really managed by NSF for us. We participate and select REU centers that are of interest to the Department of Defense. We also have, as I mentioned, lots of professional society scientific exchanges. In addition to the department's HBCMI program, we also fund an Air Force HBCMI program out of our own portfolio. We do this because we're trying to enhance the diversity of our workforce and trying to bring a more diverse approach into the scientific portfolios that we actually fund. There's a lot of interest in our Young Investigator program. I think the first Young Investigator program really came out of the Department of the Navy 25 years ago. In our case, we've been doing this for 5 or 6 years. This gives young faculty members opportunities to compete for resources designated for those who are, have received their PhDs, less than 5 years. And so again, you can find information about these on our web pages. So I just want to summarize, the fact of the matter is the nation has a strong support in basic research. We've heard, and there's a quote here from the State of the Union speech from President Obama, clearly the White House has a commitment to basic research. The Department of Defense has a strong commitment to basic research. The Air Force has a strong commitment to basic research. And what we do is, as I mentioned, is we're really trying to probe today's technology limits, which will lead us to new future opportunities, and we're trying to create a knowledgeable workforce for the future. And I'd like to mention that, you never know where these investments are going to go. And so from a personal story, my entire career was changed by a small research grant and when I was at the University of Delaware, where I had the opportunity to do research in the summer prior to starting my graduate work. And I changed my career from thinking about doing an analytical chemistry degree focused on being in industry to doing combustion sciences and actually really having more of a government career. And that small grant actually shaped my entire future. And it turns out the organization who funded that small grant is the one I run today. And so you never know where these investments are going to go. And so we're looking to support the workforce, again, not just for the Air Force, but for the contractors that support the Department of Defense, the other services, the scientific community, the academic community, because we need future academic faculty members who actually know the Air Force or know the department and can train the generation after the one we're training now. So it's a very strong program and focused on STEM activities. And what I hope I gave you at least a little bit of a sense today is this is really a fully coordinated program. We're leveraging opportunities all over the basic research portfolios. We didn't have much time to describe how we deconflict with the other services. There's not much overlap. It's very collaborative. It's very collaborative with NSF. It's very collaborative with the DE, with Department of Energy, Basic Energy Sciences, NIST. This cadre of program managers in these organizations know and work with each other on a regular basis. We hold common program reviews. We do everything, collaboratively. We review each other's proposals at times. So it's a very integrated community, which is really, in the end, trying to actually take this diverse approach to solving our national needs in basic science and actually using this diverse approach to maximize the overall discovery potential for the Air Force and for our nation. And so with that, I thank you very much for your time.
Thank you, Dr. Russell. We're now going to open it up to our audience for questions. If you have any questions for Dr. Russell, please send your email to federalupdate@missouri.edu. Again, that email address is federalupdate@missouri.edu. So we have a number of questions already.
Okay.
How are the international office locations chosen, and are there any plans for new offices in the future?
So the international offices actually have some long history. The office in London has been there since the late 50s, early 60s. The one in Tokyo was placed in, I think, maybe 15 or 20 years ago. In many cases, they're co-located. So even in the international offices, we are actually co-located with the Army and the Navy. And so it helps to actually enhance the leverage and collaboration, so we co-locate. And so we are also co-located in Santiago, Chile. At the moment, we don't actually have plans on expanding our international offices into other locations. We do think where they're currently located gives us the ability to reach into other countries. So even though we are in Japan, we fund a lot of work in India, China, Singapore, Australia. I'm sorry, we don't fund in China. I apologize. I meant Australia. We do fund some work in Hong Kong. and so Korea, and so we are reaching most of these countries through those offices. Same thing out of our European office, where we're funding a lot of countries across the European community, and we actually fund work out of the European office in Africa, believe it or not. And then the same thing happens in South America. The South American office was set up recently because really in South America it's an emerging area of science, and so we would like to engage early on in both Latin and South America, as these areas begin to emerge and develop their scientific base. And so we think of that as a strategic investment to, work with those communities and help them in science.
Thank you. How can U.S. universities get involved with these international locations, or is the work there pretty much strictly kept within country?
Not actually, no. So some of the programs, there are many ways to do that. So a lot of the ways we find researchers to engage with overseas are through the academic community here, because the fact is the community here actually has a much stronger network than we do. And so if you're in part of our portfolio, a lot of times, those engagements with program managers actually, help identify where there are other opportunities for finding the best science we can. We also have programs where, they are jointly funded. So the program in Korea, one of our programs in Korea, which is, Nanobio Information Technologies program, we actually fund efforts there with their equivalent of NSF, and they're done jointly. And so what happens is the Korean academic researchers work with American academic researchers, write joint proposals. Those joint proposals are submitted and jointly evaluated, and then the Korean agency actually funds the Korean researchers, and we fund the American researchers to actually work with them. So there are opportunities like that to engage. Probably the easiest way to begin to engage, whether it's through the international or even just the portfolios as a whole, is to engage through the program management staff at AFOSR and use that as a way to begin to evolve, the relationships as you move forward.
Thank you. Again, if you have a question for Dr. Russell, please send it to federalupdate@missouri.edu. Don't put a plural on the end of federal update. It needs to be federal update, not federal updates. federalupdate@missouri.edu. Have a question here in regards to sustainability and energy, and some research that may be conducted around that. Is there any program related to renewable aviation fuel or fuel cells that the Air Force is interested in getting proposals for?
Yes, so we've had a fairly strong portfolio in the energy area in general. I think if you noticed on that view graph when I talked about mission, you'll see it's the smallest pie. These are programs that we are actually reducing in many cases. It does not mean that we're still not interested. So we do some work in fuel cells, and so there's some biological fuel cell work in a program manager's name called Pat Bradshaw. If you go on the APN webpage I mentioned, you could search for some of these. In the aviation fuels, the focus for us is mostly not in how do I make aviation fuels. For us, it's really in our combustion program. It's really understanding the energetics of these alternate fuels and how they would ultimately change engine design. There are more applied programs in 6.2 and 6.3 that are actually looking at blends and aviation fuel and testing. And then a lot of things, we did a lot of work in algal oil, where you could do oil production from algae and hydrogen. Many of these science bases have been transitioned to basic energy sciences because it's really driven more in their mission. And so there are opportunities. We do accept proposals in these areas, but some of the larger programs are actually with the other agencies at this point in time.
Okay, thank you. Again, if you have a question, please send it to federalupdate@missouri.edu. Are there any outreach programs that you operate for STEM education in K-12?
No. The Air Force Office of Scientific Research is not doing any of the K through 12 outreach. There is K through 12 outreach in the Air Force, though. So there's a STEM office at the Secretary of the Air Force level, And that STEM office runs the K through 12 outreach, and it's run through the Air Force laboratories and logistic organizations and other parts of the Air Force, because a lot of the K through 12 engagement is really about a hands-on engagement with, the local high schools and education groups. And so it's really not about funding, it's really more about how do I actually bring people together. And so there are things through what's called the NDEP, which is the National Defense Engineering Program, where there's a lot of K through 12 funding. And so if you want to engage with the Air Force, I'd recommend engaging with the local Air Force organizations. The Air Force Research Laboratory, which I didn't mention, is located at Wright-Patterson Air Force Base, which is in Dayton, Ohio. For anybody in that area, they have very strong K through 12 outreach programs. There's our laboratory in Rome, New York. Again, they have a very strong STEM outreach programs. There are 2 laboratories in Albuquerque, New Mexico. They as well have strong K through 12 outreach programs. And then there's a laboratory in Eglin Air Force Base. And like the other ones, they have strong outreach programs as well. And then there's a group actually in Edwards Air Force Base, which is outside of Los Angeles, east of Los Angeles. And I'm not sure how much activity they have, but most sites actually have K through 12 activities.
Thank you. Again, if you have a question, please send it to federalupdate@missouri.edu. Have a question here. Faculty member wants to know if it's possible to become a reviewer of proposals, and if so, how do they go about doing that?
So it is possible to become a reviewer of proposals, and so maybe it's worthwhile, and I'll get to the proposal piece, but I don't know if someone asked this question, but I think it's worthwhile to touch on a little bit about how we function as an organization. So the department, and this is really a discussion for all 3 services. I don't know if the Navy will mention it or not when they're here this afternoon. So in the Department of Defense, the program managers actually are very actively engaged. They don't tell you what research to do, but they are actively engaged. And they really have the authority to select and not select programs. And so we use a process called a white paper process in doing our proposals. And the reason for that is because we don't want you as a potential PI, principal investigator, someone who's submitting to the organization, to spend a lot of time engaging in writing proposals in areas that you may have very little success at actually getting funded. And so what we recommend is it's really a contact sport. So the first thing I recommend is really about engaging with program managers. They will accept your email messages. They will accept your phone calls. They will talk to you at professional society meetings. I will warn you that there are only 60 of them, 45 roughly in the United States. There are probably 10,000 of you. So remember when you're engaging with them that one phone call may not get returned sometimes because they get lots of phone calls, lots of emails. But it's that beginning to understand the program which is really important, and this leads to being a proposal reviewer, because they're looking for people who are have some knowledge of the areas they're working on, but also understand the directions and things that they're doing in their programs. So some of those initial engagements may not lead to funding. They may just lead to the opportunity to be involved in reviews and other aspects of their programs. So back to the white papers. The white paper is a 2-page document, and when we submit a proposal, there are issues associated with why the Air Force would care. Why does what are the specific things the Air Force you're addressing for the Air Force? But in the white paper phase, that's not what people are interested in. What they're really interested in is, what science are you interested in working on? What are the problems? What are the challenges? And what are you going to do to solve them? And if you waste white space describing why the Air Force cares, then you're wasting space telling them what are the science things you're interested in looking at. So the outcome of a white paper is one of a couple. The first one may be that we're not interested in this, and that meant that you've spent time putting together a 2-page document. It may be that it just starts a conversation And it might be that one small section, this is really interested, I'm not interested in the rest of this other stuff, but it starts a discussion between you and a program manager, which may lead to something later. It may turn out that it isn't just that they're not interested. They may say, this isn't an area that I fund, but I do know people in other agencies who actually do this part of this type of work. So in the quantum information science area, each of us funds different aspects of quantum information sciences, and so you may submit a proposal to one program manager, and they may, a white paper, not a proposal. They may tell you to submit it to somebody at DARPA, at NSF, or Basic Energy Sciences, or ARO, or ONR, or they may pass it. Maybe that they, you sent it to them and it was the wrong person, AFOSR, and then they would just directly pass that on. And so through that feedback process, if you're asked ultimately to submit a proposal, then you're actually submitting a proposal that might have a decent chance of being funded. So the success rate of white papers is about the same success rate of proposals at NSF, but the success rate of proposals, white papers, is about the same as the success rate of NSF. I don't know if I said that correctly or not. The success rate of proposals when being requested is about 30%, which is a pretty high number. It's about 1 in 3. And it doesn't mean we don't accept proposals directly. We accept proposals without doing the white paper phase. We do all that. All the services do. We're looking for the best stuff we can find. It's just that there is this engagement process which makes a huge difference in the way you do business with the Department of Defense basic research organizations as opposed to NSF or some of the others. And it's part of this diversity of approach that I mentioned earlier.
Thank you. Again, if you have a question for Dr. Russell, please send it to federalupdate@missouri.edu. And we have time for just a few more questions, so please send your final questions in to federalupdate@missouri.edu. I have a question here from one of the small colleges that are listening today. Would you elaborate on the equipment program for academia, and are primarily undergraduate institutions successful in these competitions?
I would have to go back and look at, but I don't think there's been a lot of success in undergraduate institutions receiving DURP grants. But it doesn't mean it can't happen. I've just, from the program we have, I'm not sure that is has been successful. But I do know that there have been some there are some master's granting institutions that have received DURP grants. There are some very small PhD programs, especially in HBCMIs, that have actually received some DURP type grants or DURP grants, and then even some of the some of the other colleges. But I'm not saying it's precluded. I would have to go back and take a look. But I would guess the probability is low, right? Because in many cases they're tied to our research programs.
Mm-hmm. Okay, thank you very much. Have a question here. When foreign nationals, especially PIs from sensitive countries, service PIs, are there potential concerns that you take into account when you evaluate their proposals? And are there any restrictions that you're aware of on how research teams are organized?
So we have no restrictions on how research teams are organized. We have no restrictions on proposals of whether they're from foreign nationals. We don't actually manage, what students are on the programs, what postdocs are on the programs. That's, not, we do basic research, and we that's not part of our process of identifying, and so there is no restriction on who participates in those activities. Now, in some of the special programs, I think I'd have to go back and look at guidance, but I think YIP and PCASE, there are some green card holding requirements in some of those special programs that have been defined when they were established. I don't want to misspeak whether YIP and PCASE have them, because I just don't know for sure, but you'd have to look them up when you look at those, and those specifics would be on the web pages that identify them. But for the URI programs, which are primarily MURI and DURP, and for our basic research program, which is primarily single investigator, there are no restrictions or limitations.
Okay, thank you very much. We have a question here. Do you fund single PI small size proposals, or do they have to be large collaborative proposals?
A majority of what we fund is actually single PI. The question, it begs a further discussion about what small means small. The typical grant size has historically been somewhere between $120,000 and $150,000. We have made a concerted effort to actually increase the grant size a little bit. Sometimes that's done as a single PI. Sometimes that's done as two PIs actually, form 2 or 3 PIs forming, teams for a larger grant where, the program manager has actually trying to bring maybe an experimentalist and a theoretician together, and so they build them into a single grant. And from that, the grant sizes probably moved closer to the 200 or a little over $200,000. But it varies, right? Because a mathematician, and no offense to my theoretical colleagues, often don't require the same resources as an experimental program. And so many times we fund things at the 50K level because that's the appropriate funding for the type of work, and if they're funding just a couple of graduate students, that's what's required for the graduate students. So there's really no limitation whether it's large or small for the grant size.
Thank you. We are running out of time for questions. If you send questions that don't get answered right now, we're going to make sure they get to Dr. Russell so that he can answer them in the future. And again, thank you so much for being here. We really appreciate it. And our next speakers are coming up at the top of the hour.
Well, thank you very much. I enjoyed it, and I hope everybody got at least a little sense of what the Air Force is doing. And again, if you can check out the APAM page, I think you get a lot more information than I can provide in an hour.
Thank you.